Okay, so in 2.23, we're sort of given the statement that given two delta functions, d1 and d2, they are equal, assuming that these two sort of equations are equal. So when applying an integral from negative infinity to infinity of some well-behaved function f of x multiplied by this delta function, if this is equal to the same thing with delta 2, then delta 1 by necessarily has to be equivalent to delta 2. And in part A, we are asked to show that this is true. So our two delta functions are d1 equals a Dirac delta of some constant c multiplied by x, and then d2 is equal to 1 over the magnitude of c multiplied by delta x. So basically, our goal here is to take d1 and d2 and plug them into these integral equations and see that the result is the same. So let's start with d1. So we have an infinite integral, negative infinity to infinity, of f of x multiplied by a Dirac delta cx dx. So sort of the first thing that we do is we recognize the fact that the deltas, when in an infinite integral, will always sort of snipe out specific values. So in this case, this Dirac delta is only non-negative, or it's only non-zero when x equals to 0. So what this is going to do is this is going to snipe out f of 0. So this will become an integral from negative infinity to infinity with our f of 0 pulled out to the left, multiplied by a Dirac delta cx. Now, this is a bit of a problem, because we know that the integral from negative infinity to infinity of Dirac delta x dx is equal to 1. But we don't know if this is still necessarily true for a Dirac delta of cx. Sort of intuitively, it seems like they should be, because they both sort of have this identity of being 0 everywhere except at x equals 0, where it equals infinity. So it seems as if sort of they should both equal 1, but that isn't necessarily true. This constant at the front actually does sort of alter the properties of the delta function somewhat. And to see exactly how it does this, what we can do is we can sort of utilize a u substitution. So I can forcefully turn this into sort of something that looks exactly like this by sort of defining a new variable. So let's call it u, and we'll say that u is equal to cx. So in which case, if we use u sub, then du is going to equal c dx, or dx is going to equal du over c. So if we do that, then what this is going to give us is that this is actually going to equal f of 0 times 1 over c multiplied by their integral from negative infinity to positive infinity of Dirac delta u du. And this does equal 1. So what we see here is that it actually doesn't equal 1. This Dirac delta of this function doesn't actually equal 1. It actually equals 1 over c because of this extra factor of c here. So what this actually equals is f of 0 over c. Now, there's an additional problem here, and the problem actually gives us a hint, which is that we have to check the case where c is negative. So if c is negative, then what we get is that, here, let's do this in green. So if c is negative, what we get is that the integral from negative infinity to positive infinity of f of x of Dirac delta negative c x dx, so we're just attaching a negative sign at the front, is then going to equal negative f of 0 over c. So this is what would happen if c were some sort of negative constant. So the issue that arises here is that the fact that these two terms aren't actually equivalent to each other. The reason why they should be equivalent to each other is because Dirac delta of negative cx is mathematically identical to Dirac delta of cx. If we look at what they actually equal, right? Dirac delta of cx is equal to 0 when x doesn't equal 0, and infinity when x does equal 0. Adding a negative sign in front of the c doesn't change this property. So mathematically, Dirac delta of cx is effectively the exact same as Dirac delta negative cx. So actuality, there is an equivalence between this top statement and this bottom statement. And the fact that these two results don't equal is sort of a problem. So what we have to do to resolve this issue is we have to take the magnitude of c instead. So what we actually say, sort of instead of f of 0 over c, is that this resulting expression has to equal f of 0 over the magnitude of c. And we do this, once again, to sort of resolve this issue of c sort of the Dirac delta giving us a different answer when c runs negative, which it should not do, because once again, Dirac delta of cx is effectively mathematically identical to Dirac delta of negative cx. This seems sort of like we're pulling out this absolute value out of nowhere, and it kind of does. And the reason why this sort of feels really weird is because, once again, the Dirac delta isn't necessarily a function. It's a very weird behaving artifact that we sort of invent and sort of assume have certain properties. So because of that, because of the fact that the Dirac delta has a few properties that are sort of necessarily true, and it's not an actual naturally occurring function, it's sort of a it's a man-made thing. In the same way that sort of imaginaries were invented to allow square roots of negative terms, the Dirac delta is sort of it's an artificial creation that we use because it helps us with certain mathematical systems, and the reason why it has this weird property of introducing this magnitude here without warning is because sort of we need it to satisfy one of the properties of the Dirac delta, which is that, you know, the Dirac delta of negative cx has to equal Dirac delta of c at positive cx. So because of that, we introduce this magnitude term. Next, let's do d2. So we have the integral from negative infinity to positive infinity of f of x multiplied by 1 over magnitude c times Dirac delta x, because this is our d2. Well, in this case, same thing happens. F of x gets pulled out as f of 0, and we have f of 0 over magnitude c, and then we have our integral from negative infinity to infinity of Dirac delta of x dx. This is just 1, so what we're left with is, you know, the exact same term as we have up here. Therefore, d1 does indeed equal d2, and we are done with part A. Okay, part B has us say that, okay, we have this step function equation, theta of x equals 1 when x is less than 0, and theta of x is equal to 0 when x is, or sorry, it's 1 when x is positive and 0 when x is negative. We can draw this if we want. So when x is positive, theta of x is equal to positive 1, so it's just a line like this. And when it's less than 0, it's just a flat line parallel to the x-axis. And we are trying to deal with the derivative. So d theta by dx is equal to, and if we look at this, well, when it's positive, it has a slope of 0, and when it's negative, it also has a slope of 0. So d theta by dx is just equal to 0 when x is not equal to 0. When x is equal to 0, it has a discontinuity jump, which implies that the derivative is actually infinity. So when x does equal 0, this is infinity. This is literally just the definition of a delta function, because our Dirac delta function is literally defined as 0 when x doesn't equal 0, and infinite when x does equal 0. I'm not too sure why this is even a question in the first place, because this is just very obviously true, but so be it. This is part B.